Hello everyone, this is Nivedita Khole from MIDAS IT. This video is on Seepage-Slope Coupled analysis using MIDAS SoilWorks. It's a geotechnical 2D solution for practical design. In this video, we are going to have the product overview, general strength of SoilWorks. Seepage analysis will be demonstrated. We'll have a discussion on Seepage-Slope Coupled analysis, and we'll also perform a slope stability analysis and design using SoilWorks. And after this, we are going to have a small summary of this video. We'll start with the product overview. SoilWorks is all-in-one 2D finite element analysis and analytical software solution for structural and geotechnical engineers. SoilWorks contains 7 modules. Slope module for slope stability analysis using strength reduction method, stress analysis method, as well as limit equilibrium method. Then rock module for different failures and slope stability of rocks. Then foundation module for PY analysis for various configurations of piles. Then dynamic module is for seismic analysis with a huge database of time history records of major earthquakes. Then seepage module is to analyze the effects of seepage to determine the pore water pressure, phreatic line and flow path. Soft ground module is for immediate settlements in sandy soils or consolidation settlements in clay soils over a long period of time. Ground module is mainly for tunnel lining design and can be used for analyzing the effects of cutting and filling. Therefore, all in all, SoilWorks covers all the practical geostructural analysis requirements in a single software solution. Let us check the general strength of SoilWorks. Generally, in any software, structural and geotechnical engineers run numerical analysis with following workflow, such as geometry modeling, meshing, loads application, and boundary conditions, and then further perform the analysis and then go ahead to check the results in the post-processing. This workflow has been arranged in SoilWorks such that the user can move from left to right, start with the modeling and end up with the results. That's how intuitive MIDAS SoilWorks is. Numerous project applications and verification examples support the reliability of the software. Now, where does SoilWorks have an edge over other programs? To explain that, SoilWorks has 7 smart features as shown over here. Let's have a detailed discussion on these smart features. Smart modeling, wherein you can use all commands of CAD-based software. Shortcut keyboard commands are also available. Also, you can even copy-paste the drawing from CAD directly in SoilWorks. Now that the drawing of our model is ready, all the surfaces to assign the properties of soil can be generated with one single click. And that is what Smart Surface will do. It will automatically create surfaces. Smart meshing, wherein without much of a manual effort of sizing the mesh, MIDAS SoilWorks automatically works it out according to the model requirement. No worries with nodal connectivity, thus eliminating errors as such. Smart support, that takes care of the most usual boundaries applied to constrain the ground automatically. The Smart Technical Review is your friend to caution you of possible errors before analysis, even if you have missed out any additional step anywhere. Smart Analysis is sure to make you feel relaxed, as using only one single model, one can perform analysis for all cases simultaneously. Lastly, Smart Results can provide you with high quality report within few minutes. Let's go ahead to seepage analysis. So let us see the seepage analysis definition, then we'll have a discussion on seepage numerical analysis. Then we'll have a demo on SoilWorks, using SoilWorks on Seepage, and then we'll have a short summary for the seepage. Seepage basically occurs along the waterway that connects through the empty pores between soil particles. This seepage is influenced by various factors. The soil properties such as porosity, particle shape size and degree of saturation, then mechanical properties such as inner settlements. Thermodynamic properties such as viscosity and freezing thawing also is influential, and even the chemical properties. So let's go ahead to see the seepage numerical analysis. Seepage analysis is divided into steady state analysis and transient state analysis. In steady state, it is assumed that the ground is saturated, and as a result, this method draws a relatively large external forces. Whereas in transient, it is assumed that the boundaries vary with time. The ground, as time passes, gets back in unsaturated state. This variation of moisture content and porosity with respect to time is taken care by the transient analysis. So the main difference between steady and transient analysis is nothing but the boundary conditions that change as time passes by. SoilWorks uses Darcy's law to express the phenomena of seepage, which exists in the saturated and unsaturated soils as shown over here. The difference between saturated and unsaturated soils is that the coefficient of permeability that varies with water content, and this water content varies with pore water pressure as shown in this graph. So indirectly, the coefficient of permeability changes with respect to pore water pressure. Let us go to the SoilWorks to actually feel its strength. When we open SoilWorks, the first thing we see is the different modules available in this single software, that is SoilWorks. We have ground module, slope, soft ground, foundation, seepage and dynamic. In this video we are going to be using the seepage module and the slope module. We'll start with the seepage module first. By clicking on seepage module, a new file will automatically be opened up, and the first thing that prompts up is the unit system. So there are predefined unit system, that is SI, CGS, FPS unit systems. We can also have user defined unit system. So I'm using kilonewton, meter and time in seconds. Okay. Then we'll talk about the user interface of MIDAS SoilWorks. Basically all MIDAS softwares has got the similar type of user interface, but as discussed earlier in the presentation, there are different tabs in SoilWorks arranged as per the workflow. Like, first we do the geometry modeling, then we go ahead mesh the model, then we go ahead provide the boundary conditions, analyze the structure, and then check the results in the result tab. So from left to right, you're done with your entire project. After that, there is works tree. Works tree is a very intuitive feature in SoilWorks. At one glance, you can understand what all things have been incorporated in the model. We also have the results tree after the post-processing mode has activated. Then is the message window over here. There is message window which provides you with any errors or warnings. You can even use your CAD commands in this message window. Let us start with the modeling. We have got smart modeling feature in MIDAS SoilWorks. Smart modeling, wherein you can use all the CAD data directly from a CAD file into SoilWorks interface. And also you can import the CAD file. CAD file in the form of DWG, DXF, .dgn, all are available. So in this video we are going to be importing the CAD file. As you can see here, the model geometry has been imported entirely with different soil layers. And the levee, this is the levee that we are going to be working on for our seepage analysis, and also we are going to use the same model for the slope. We have to create surfaces for each and every soil layer. However, in SoilWorks we have got a smart feature, that is the smart surface. Using the smart surface, by just one click you can create the surfaces for all the soil layers. That's how fast MIDAS SoilWorks is. After creating the surfaces, we can go ahead to the next tab, that is model. In this we are going to be defining the material properties and structural properties. Now here we are having only the ground material properties or the grounds layers. That's where we're going to be defining the ground material properties. Now in MIDAS SoilWorks, in Seepage we just have to provide the horizontal permeability coefficient, vertical permeability coefficients, then water content, unsaturated properties, effective porosity, and specific storage. That's it. I mean, it's for an analysis, the coefficients and the water content are all that is required. So we provide with the name, we provide with the property information, and also the unsaturated property function is to be created. So we can just simply check on unsaturated property and create the unsaturated property, wherein you have to provide the function data, the permeability function data as well as the water content function data, as discussed earlier. In this permeability function data, you can see over here that there is Gardner coefficient, then frontal function, and Van Gennep 10 is available. Also you can have a user defined function. You can simply copy paste from your Excel sheet over here and create your permeability function data. Similarly, water content function data is available, which is the graph of water content with respect to the pore water pressure, the pore pressure head, and this is the pore pressure with respect to permeability ratio. So exactly we have got the function types, Van Gennep 10 and user defined for the water content function data. Now this entire information we can manually input. However, in this video, for a quick demonstration, I'm going to be importing from a file which also has already the information of the entire ground material properties. So that is also another way in which you can define the ground material properties, that is by using a previous model database. So once you create in one file the entire database, you can just simply import it. So that's I click on import data. So in the works tree you can see over here that the ground material properties have been imported from the previous model file. Now all I have to do is assign these defined material properties onto the surfaces. That is a very easy process in any of the MIDAS softwares, assigning by just using the drag and drop tool. That is, you select the surface. I'm selecting weathered rock, the lowermost layer, and I drag and drop the weathered rock layer property anywhere on this user interface, work interface. So I'm going to do that for the weathered soil layer, drag and drop. Then there is alluvial layer, the existing levee, embankment layer, and finally the riprap. We can see that by expanding these layers, if the embankment layer has been assigned successfully to the surfaces that had been already selected. So we can just right click and say select, and we can see that yes, embankment layer has been assigned correctly to that particular surface. Okay, so our ground material properties have been assigned. Next thing that we're going to use is another smart feature of SoilWorks, that is Smart Mesh. You do not have to have any proficient knowledge of the sizing of elements for meshing the entire model. All you have to do is click on Smart Mesh, choose what type of mesh you would like. I'm selecting very fine mesh for this video and click on OK. There you go. As you can see that the mesh size has been slowly decreased, or has been decreased at the locations where the boundaries have, as in wherein the geometry has changed. So you do not have to worry at all about the sizing of elements in that case. And we are now good to go ahead with the boundaries. So I go to the boundaries, that is the next tab after the modeling, the next tab, and I'm going to have the nodal head. So the nodal head I'm going to define for both transient and as well as steady state, because we are going to perform both the analysis cases simultaneously. And firstly, let's start with left steady state nodal head, and we can apply the nodal head on the nodes. However, MIDAS SoilWorks has got even the selection of curves for assigning the boundary condition. So curves are nothing but the lines that we have created using the drawing tools. So I click on select curve and I select all these lines, and then I provide with the nodal head value, which is 18.42, and then I click on apply. Now to go ahead and provide the transient state nodal head, I do not have to delete any of the lines, delete any of the left steady state boundary condition at all. No, I can just simply go ahead and define my nodal head for the transient state. Left transient state, because we are going to have this particular nodal head on the reverse side of the levee, so that's why I've called it as a left transient state. I'm going to select the same curves that I had selected for the steady state analysis. Then the nodal head. Now in case of transient state analysis, the nodal head is going to change as per time. So here the value will be as a scale factor, so I'm going to keep it as 1, and then I'm going to define the function. So for that I'll click on FE. Now I've already over here imported the function from a previous file, so we can see over here just we have to provide the name and then time in. I've used the seconds, as we have seen at the beginning of the demo, that we have used the seconds, time in seconds. So I've provided the time in seconds. At 0 it's going to be 15. At after 18 hours we are going to have 129,600 seconds. It's going to be 18.42, and then further it's going to stay like that for 48 hours, that is 172,800 seconds. Later it's still going to be at 18.42, and after completing 3 days, that is to 59,200 seconds, it's going to get back to 15. So we are going to be using this function for our transient state nodal head boundary condition. So for that I'll just select the water level change function and I click on OK. Okay, so after providing nodal head, we can provide a review with the review boundary. So I click on review boundary and I create boundary set name as review, and then I'm going to be using the curves. Click on select curve and I click on all these lines that is at the protected side of the levee. I've selected 6 curves and I click on OK. So this is how easily your nodal head and review boundary conditions have been applied to the levee, to the entire model. Now I can go ahead and perform the analysis. Firstly, I create the analysis case because SoilWorks has got smart analysis feature. So in smart analysis feature, I can have two analysis cases run simultaneously. So I have steady state analysis. So analysis method Seepage steady state analysis, I click on use all mesh sets, and I'm going to be using the boundary conditions as left steady state and the review. I click on apply to define the next analysis case, that is the transient state analysis case. I click on seepage transient analysis. I'm still using all the mesh sets, but however boundary will be now left transient analysis and review. Then I have to also define the time steps for transient state analysis, so I click on the analysis control data, and then I can have firstly the recheck by maximum pressure, increase in pressure. These are potential seepage phase options available. Then the time steps that I have to define, so I click on auto generation. I call this as 259200. This is a 3 days period and I want it to be divided into 4. I'm actually trying to match this with respect to the function that we have provided for the transient state boundary condition, nodal head boundary condition. So to match it, everything is same except for the third one, which is 172,800 seconds, and I click on OK and click on OK again. Okay, so that steady state and transient state analysis and cases are created and ready for us to go ahead with another feature, that is the smart technical review. So I go to the tools and I go and check if the analysis is good to go ahead. So we can say checking the boundary of analysis model, then ground material data if it's been rightly done, boundary conditions have been applied. Then if at all you wanted to apply the loads, that also is possible, construction stages if you want to. It's in red, it's just because if in case you have missed it, you can just try and go ahead, apply the loads or create the construction stages. Now the part that we need to find is analysis can now be performed. Okay, so this information is provided before you perform the analysis so that there will be no errors after you click on the perform analysis. So your time is saved and you can be very sure to go ahead with the analysis. So I go to the boundary analysis tab and click on run analysis. As you can see over here, 2 analysis cases are there and I'm going to run them simultaneously. So I've checked on these 2 boxes and then I click on perform analysis. Okay, so our analysis has been performed and we are good to go ahead and check the results. We are in the post-processing mode, that's why the software has automatically taken us to the results tree menu. Here we can see the different results that we require. Let us check firstly the ground element seepage results. So we have total seepage velocity. In the steady seepage analysis, this is the maximum. To find out what is the maximum, you can check in the legend available over here, or you can also tag the maximum value. So I'm going to use tag and I'm going to click on maximum. So I have got the maximum value as 2.73 10⁻⁻⁶. Then I can compare this total seepage velocity with the transient state analysis total seepage velocity. So I'm going to go for the first time step, that is 64,800, and that is when my nodal head was 15. So I'll just check what is my total seepage velocity over there. So as you can see over here, it is exactly 1/10 of the value. So this is how you can compare the 2 values, the seepage state analysis and the transient state analysis results. So you can see over here the maximum value for the transient has been obtained on the upstream side. So this is how you can get even the total hydraulic gradient. You can get it and you can compare it, compare the 2 results, and you can check also the total head, the pore pressure head, the pore water pressure. You can also check the phreatic line. And this, in the transient state, you can do it for each and every time step. So you can check the phreatic line. It's changing with each time step. And finally, it has gone down. Also, MIDAS SoilWorks shows the flow path. So right over here, I can check the flow path for steady state. I can select certain nodes at which I would like to see the flow path. And I can check the flow path after defining them, after defining the nodes for the transient state analysis as well. So there are different time steps which we can choose from and see how the seepage is taking place. All these results can be saved using Smart Result feature of MIDAS SoilWorks. You can take images of this and you can save it in Word file. So I can just click over here, select this phreatic line of the steady seepage, and I can check on all the phreatic lines because this is what I would like to see. Okay, and also you can compare with the pore water pressure, and I can say save as Word. So you do not have to say print screen all the time and create the entire Word file. So I can go back to where I have created this particular model here. Yes, so we can see over here all these images provided to you by this software. This is for the last time step, pore water pressure, and this is for the steady state pore water pressure. Okay, now this pore water pressure result is what we need to be taken to the slope module for performing our slope stability analysis. So before we discuss about the Seepage-Slope Coupled analysis, let us have a summary of what we have found from the seepage analysis. What are the results that we have got? So we have seen the flow velocity, the total seepage velocity, and the total hydraulic gradient, and we compared them with the steady and the transient flows at different time intervals. Then we also have seen that the steady seepage condition was resulting in exceeding recommendation. So the result that we need is the pore water pressure from the seepage module to slope module, and we are going to perform the slope stability analysis at the river side. So let us discuss about the Seepage-Slope Coupled analysis. So here is the strength of SoilWorks to conduct Seepage-Slope Coupled analysis. The difference in waterheads due to transient analysis needs to be considered for both seepage and slope stability analysis. That is why the results from seepage module are going to be taken to slope module, and that is very important, which is very well supported by MIDAS SoilWorks. In seepage analysis, the effect of rainfall intensity and duration or steady and transient flow due to water storage can be considered. Using that, we obtain the pore water pressure, which is then sent to the slope module for the limit equilibrium, strength reduction method, or stress analysis method to get what we need, the factor of safety, stresses and deformations, and that is all considering the pore water pressure result. So let me explain you about the importance of performing the Seepage-Slope Coupled analysis. Now in this terrain, when rainfall occurs through precipitation, practically the water infiltrates through the permeable layer. However, it cannot further seep through the next nearly impermeable layer. This causes a temporary saturated zone leading to poor water pressure at the slope, destabilizing the slope. If the engineer does not perform seepage analysis, the terrain is assumed to be completely saturated upon precipitation due to rains for slope stability analysis. However, if the condition exists like this one, as shown here, then assuming the fully saturated soil is incorrect. The engineer has to perform seepage analysis to get the actual pore water pressure for slope stability calculations. So the analysis flow for seepage-slope coupled analysis is as shown here. You perform seepage analysis including steady state and transient state. Take the results to perform the slope stability analysis, in which you can get the deformations and factor of safety by SRM. Not only that, but you can also perform stability analysis by LEM considering the pore water pressure taken from the seepage analysis. Now that's something very new. Comparing the results between the slope stability analysis, here, case 1 where all soil layers are considered to be fully saturated with no seepage results considered, and the case 2 wherein we have considered the seepage results. Here we see that the factor of safety for fully saturated condition is obtained to be safe. However, the factor of safety for case 2, where we have considered the seepage results, the pore water pressure, the factor of safety is lower than the permissible value. The slope is found to be failing, and further the engineer can decide to apply the nails, that is for stabilization, whereby the factor of safety shall be satisfied. Thus, by considering the fully saturated condition for all soil layers, the factor of safety obtained is incorrect, since we can see that by considering the seepage results, the slope is still failing. Let us go ahead and discuss about the slope stability analysis and design that can be performed in MIDAS SoilWorks. In this, we are going to be seeing the definition, checking the design procedure in SoilWorks, then the limit equilibrium method, the continuum based methods, the slope stabilization that is available in SoilWorks, and we'll have a short demo after that using the same model of the seepage analysis in MIDAS SoilWorks. So, starting with the definition of slope stability. Slope stability is nothing but the potential of the soil covered slopes to withstand and undergo movement. Stability is determined by the balance of shear stress and shear strength. That is a factor of safety, right? The field of slope stability encompasses static and dynamic stability of slopes of earth and rockfill dams, slopes of other types of embankments, excavated slopes, and natural slopes in soil and soft rock. Sudden and catastrophic failures of slopes leads to injury or loss of life, and it also disrupts the road or rail above it. Let us see the design procedure in MIDAS SoilWorks. The design procedure for soil stability or slope stability analysis in here can be performed by both analytical as well as continuum based methods. The continuum based method includes strength reduction method and the stress analysis method, whereas the limit equilibrium method is the analytical method in MIDAS SoilWorks, which has all these failure criteria as shown over here. MIDAS SoilWorks also supports reinforcement in the form of anchors, nails, piles, geogrid, struts, etc. And finally, in SoilWorks, a detailed design report is generated comparing the design factor of safety. Let us see more about limit equilibrium method in MIDAS SoilWorks. Basically, it is a method of slices in which the failure surfaces are divided into numerous slices and equilibrium of forces and moments is checked for the slope stability calculation. The input data for soil layers is cohesion and angle of friction. Boundaries defined are arc, polygon, auto search. Arc is as shown over here in the bottom left corner. Is where the user specifies nodes or center in which various failure circles can be drawn, and factor of safety for every circle will be calculated. The other method is by specifying the polygon. The user specifies the polygon itself onto which the factor of safety will be calculated. Okay, so third option is auto search, in which we can search automatically for the failure surface. We don't need to define the centers or the polygons. There are other boundaries like the cut failure surface by arc passing, or arc passing limit can be provided. SoilWorks also supports tension crack. Considering tension crack, what the software does is the slices having tensile normal force are ignored for factor of safety calculation. So as you can see here, the tension crack is defined. Beyond this, the slices are not considered for calculation of factor of safety. That is more accurate factor of safety calculation. The loads are line load, static seismic acceleration. Analysis results are factor of safety in critical section. Now the advantages in limit equilibrium method is that it is simple theory and has been verified by numerous successful construction cases. The cons in LEM are no strain displacement compatibility, and there is no displacement and stress output. All cons could be overcome by using the finite element methods, which is also supported by MIDAS SoilWorks. Let us discuss the simplified and advanced analysis methods available of limit equilibrium method in SoilWorks. Simplified are the Fillenius, Bishop's and Janbu, which are quite old. Bishop's disadvantage is that it doesn't consider the horizontal equilibrium, whereas Janbu does not consider the moment equilibrium. These are the drawbacks of the older methods. Advanced analysis methods include the Spencer, MNP and Surma. These consider all sorts of equilibrium, and they give much accurate results compared to Bishop and Janbu. Let's discuss the strengths and weaknesses of LEM based on which of different LEM methods, based on which engineers can make a choice for the analysis method. So Bishop and Janbu are simplified method, like I said earlier. The time taken in these cases is less, but the results are inaccurate when it comes to horizontal loads. For Janbu, the results are too much conservative. With advanced analysis methods like Spencer's, MNP and Surma, the analysis time is longer, but the factor of safety calculations are quite accurate, and these are well supported by MIDAS SoilWorks. Let us see about continuum based methods now. Like we discussed earlier, limit equilibrium method has limitations which can be overcome by continuum based methods. So LEM cannot provide us the stresses and deformations in the ground layers, so we need finite element based methods like this strength reduction method and stress analysis method, which has benefits from both LEM and this SRM method. So SAM has got benefits of both LEM and SRM methods. Okay, now let's talk about the slope stabilization after finding out the slope has failed. So when we find the factor of safety of the slope is unsafe, we can use reinforcements like anchors, nails, all of which are well supported by the SoilWorks. Let's go now back to MIDAS SoilWorks and have a short demo on slope stability analysis. Go directly to the slope module. We save this under the slope module. A warning comes up wherein you need to define the material properties for the limit equilibrium method. The continuum based method properties are already there. We are going to perform only the limit equilibrium method. So what I'll be doing is I'll be deleting the ground material properties. I do not need these, not the mesh either. And we need only the layer sets. Then under the boundaries, I do not need these seepage boundaries. And under the analysis cases, I do not need these seepage analysis cases. So I go ahead now with defining the ground material properties. So as seen earlier, there are three ways in which you can define the ground material properties. One wherein you can manually input the parameters like the unit weight, saturated unit weight, cohesion, internal friction angle. These are only required properties for the limit equilibrium method. You can import from a previously created model file, slope model file, or you can go ahead, lastly the third one, with the database available in SoilWorks, which we're going to do in this video. So we're going to select the model type as more column, LEM, and let's say schist, and I'm just randomly selecting these four soil material properties, ground material properties. Also I can make changes over here, like let's say the cohesion is 15 kilonewton per meter square, and I click on assign. So here you go, we are done with the ground material property definition, and I can now go ahead with assigning them to the layers. So I'm going to use a selection for the surface. Going to select a surface like we did earlier by using just this drag and drop. Anywhere in this work interface, the property will be assigned. So I select the weathered soil, drag and drop. I select the alluvial layer, drag and drop. And lastly, I'm just using quickly the landfill layer for all the remaining layers. Okay, so once this is done, I can go ahead now define the boundaries. Like discussed earlier in the presentation, that there are different ways in which you can define the failure arcs, and the factor of safety will be accordingly calculated by the software. So in this video, we are going to be seeing the arc failure surface. We'll define the arc failure surface, wherein let's say we'll provide the name of the boundary set, arc failure surface. Then we'll draw a grid range. A grid range having 0.5 mesh. I'll just click over here to draw the grid range. Okay, and let's draw a grid range wherein these all nodes lying in the grid range will be the center of the arc, and from here the factor of safety for each center of the arc will be calculated. So the center of the arc might have different radius, so we are going to use either the tangent lines, or we can go ahead with the arc radius method. So I'll be using in this video the arc radius method. So here we have limitation to the arc radius, so from where exactly the software is supposed to start with the arc. So either the shortest radius, or I can go ahead with the passage point. So I'm using the passage point and defining the passage point by clicking on this box and then clicking over here on the model, so that it will intuitively take the exact point. So here we have taken this point, and then the number of arcs from here I would like it to be 10, and then I click on OK. So you can see over here, for every node these many different arcs are formed, and the factor of safety for each will be calculated, and the least factor of safety, we'll see that after the results have been provided. Okay, so after this we'll go ahead to the loads boundaries. Now, so these are general boundaries. So in the loads we are going to assign the sulfate. So here we have the sulfate load set, and we provide over here the scale factor and the z direction as -1 downward. So okay. After the load sulfate, we are going to go ahead and extract the results from the seepage analysis model that we had done earlier. So here result from other case would be clicked, and then I open the model file. This was the model file which was analyzed for seepage analysis. I open it, and as you can see over here that the steady flow and the transient at different time steps is shown over here. So these all pore water pressure results can be imported and used in the slope stability analysis. So as an example, I'll start with the steady flow and I import the results, close it. You can see those results over here under the loads. So steady flow seepage analysis result. Okay, so next thing what we're going to do is go to the analysis design tab, and we are going to create analysis cases. So as discussed earlier, the requirement of seepage-slope coupled analysis will be demonstrated right over here itself. Why do you need to do the seepage analysis? So for that I will have LEM with pore water pressure. Okay, here in the analysis control data we have different methods as discussed earlier. You can, according to your model requirements, you can select the analysis method. Most commonly used is Bishops, so I'll be using Bishops, and then I click on OK. So I'm going to use here all the mesh sets, all the boundary sets, and all the load sets, and then click on Apply. Now, as seen earlier, two or more than one analysis cases can be run simultaneously. So I'm going to run another case in which I'm not considering the pore pressure. So here I'm not going to have this result. I'll put it back over here and then click on OK and close. And I'm analysis design and going to perform the analysis both at the same time. So I click on perform analysis. And there you go, our analysis is completed. Close, and we are in the post-processing mode. So in the post-processing mode we have got over here the results tree. So also we can go to the results tab and we can view different results at the same time. But here in the limit equilibrium method, let us check what is the factor of safety that we have obtained. So with pore pressure, the factor of safety is 2.2, and we can as well see the arc failure surface. So this is the phreatic line, as you can see, imported from seepage analysis, and 2.2241 is the factor of safety. And over here this is method of slices, as we have discussed earlier, so we can get the equilibrium of forces for each and every slice. And as you can see over here, the pore water pressure has been included. Okay, so 2.22 for the pore water pressure slope stability analysis, which is quite safe. Then we can see now without pore water pressure what is the factor of safety. So that comes to 3.05, and we can check the arc failure surface over here. And as you can see that if you just double click over here, you can see that the pore water pressure has not been included. That means we have rightly defined the analysis cases, that's all. Anyway, so that's the difference. If at all you do not consider the pore pressure, then you get a higher factor of safety. If you consider the pore water pressure, then you get lower factor of safety. So it is very important to use the pore water pressure. Otherwise, if in case the factor of safety is below than the limiting value, then you will have to go ahead with the soil stabilization. So this result can also be taken as a smart report. So we have got over here in the analysis design options where we can define the limiting factor of safety. So I'm going to be using embankment slope. We also have cut slopes in the dry and wet seasons, so I'll be using 1.3 embankment slope and click on OK. And then I can go ahead with the Smart Report option of SoilWorks. Close this, and so I'll double click over here, and as you can see over here, applied safety factor is 1.3, and now it is going to check with the results. So with pore pressure, as in the comparison between two analysis cases is done automatically by the software. That's how smart the report is. It has checked with the pore pressure, drawn the arc for one case, and also drawn the arc for the second case, and also provided over here the scale of analysis safety factors, the minimum analysis safety factors, and evaluation is also provided if it's okay or not good. Video. Basically, why SoilWorks is beneficial for geotechnical as well as structural engineers. Well, coupling of slope module with seepage module is possible in SoilWorks. That is because the seepage slope stability analysis can be done by taking the pore water pressure from the seepage module. Then in slope stability analysis, we saw that both analytical as well as finite element based methods can be used. That is the LEM, SRM and SAM method. Then we also discussed how advanced and accurate analysis methods are the Spencer's, MNP and SERMA, very well supported by MIDAS SoilWorks. Then for the slope stabilization, like after there is a failure by if the factor of safety is going below the limiting factor of safety, then we can go ahead with the nails, anchors, piles, geogrids, struts, etc. in SoilWorks. Lastly, and most importantly, single model file for complete analysis and design at one section is done in SoilWorks, wherein it makes the work quick, easy and time saving. Increased efficiency is obtained, and we also get the detailed report for all the analysis cases and design results at one section within a few minutes. I would like to explain about the unparalleled services available at MIDAS. You can have easily accessible technical material 24/7 online library. You have tutorials in there, different manuals and FAQs. Also, you get ultimate technical training, as in we have the training programs, we have monthly webinars, and you can be invited and you would be invited to countrywide seminars and workshops. The best technical support MIDAS claims to have, with online chat, immediate help desk and on-demand meetings. All in all, time is money, and I say SoilWorks is time. Thank you very much for watching this video. If you have any technical queries, you can write to us at techsupport@midasit.com.